go into any detail, maybe just a reminder in terms of what the IDC's primary mandate is, and that is really the development of industrial capacity, which involves facilitating sustainable direct and indirect employment, promoting entrepreneurial development, supporting the transformational impact of communities and development of Black industrialists. We also aim to grow sector diversity so that we are not heavily reliant on too few sectors, but also at the same time, we hope to increase localized production. We also aim to improve regional equity, including the development of South African rural areas, underdeveloped provinces, and economic development in the rest of Africa, which also involves promoting environmentally sustainable growth. In terms of the call itself, it's going to take the shape of collaboration, where we are going to be working with partners to bring about the transformation and growth of an inclusive economy. This enables us to extend the reach of the IDC to where funding is needed with the requisite diligence and speed. This fund, the IDC, is making 200 million rand available to assist townships and rural businesses to weather the impact of the energy crisis. The SIPs, the kind of SIPs that we expect to be putting together applications, must have the ability to implement the program and work with energy solution installers to ensure that the energy requirements of the intended beneficiaries are appropriately and correctly assessed, such that appropriate solutions are then procured and installed. Grants are to be utilized to provide capital equipment, limited operational expenses, technical support, and training to end beneficiaries. The IDC will also consider grants for innovative aggregation solutions, which is to say that any solutions installed might be in a position to help more than one business. So we've issued this call, which will close on the 11th of November. If an application is put through and is successful, we will then contract with the qualifying SIP to distribute the funding. We expect the SIP to be in a position to identify and engage with SMMEs, implement solutions, and report back to the IDC over a period of at least the following 1 year after approval. The applications, we expect that they're going to be coming from all provinces. There is no particular provinces that we are targeting. However, as I said, if there are underserved provinces that you are targeting, that obviously will make your application more competitive. Some of the competitive features that we are looking to have in the applications is co-funding, where we expect applications to raise additional funding to put together with the funding that they're applying for from the IDC. We'll also be looking at transformation in terms of SIPs that have Black and or women youth ownership, as well as at management level. We want SIPs that have experience in the energy sector. We're looking at impact in terms of both value and number of grants towards women and youth. Some of the eligibility criteria that is applicable is SIPs that are South African owned and registered must have the appropriate licenses, must have been in existence for a minimum of 3 years, must have at least a triple BE level 4 certificate, must have adequate governance structures in place. The maximum grant amount that a SIP can apply for is 10 million, whereas for end beneficiaries is 250,000. End beneficiaries, as I said earlier on, are envisaged to be small and micro businesses directly affected by the energy shortage. We want to see proven capacity and experience in terms of program management. We want SIPs to demonstrate the ability to onboard relevant end beneficiaries, submit a list of a pipeline of potential beneficiaries, such that 50% of those are able to take at least to take 50% of the amount that would have been approved. We want to see appropriate partnerships, as well as the ability to provide training on the solutions provided. The applying entities must have audited financial statements that are not older than 6 months. Some of the terms that are applicable are that the assets procured through the funding that would have been approved will be owned by the relevant end beneficiaries. The IDC will reserve the right to monitor the implementation through either its own resources or through service providers. We want SIPs that are socially and environmentally responsible and have the appropriate ESG policies. We will also reserve the right to participate at governance level in terms of where decisions are being made in terms of the allocation of grants. SIPs will be allowed a maximum fee of 15% of the grant amount. This is a maximum amount. Obviously, if you charge less, you probably would be looked at more favorably, but the allowable maximum is 15%. Reporting, we will be expected to report on a monthly basis. At the discretion of the IDC, we can also commission audits, external audits through the relevant service providers. Some of the documents, I won't necessarily go through the list, but the presentation will be made available to you, and so you can find the list there. Once the application has been submitted through the address that is on your screen there, there will be a 3-phase process. We'll shortlist, which is really to look at compliance and some of the FICA requirements. If you make the shortlist and your application is complete with all the relevant documents, the phase 2 will then involve a due diligence process, where we might require further information from yourselves. Following that, there will be a presentation then to the IDC Evaluation Committee, whose decision will be final. So thank you very much. I think you can also find the information and the application forms on the address on your screen. Thank you so much.
Thank you very much, Dumisani. Ladies and gentlemen, you will find Dumisani's presentation in the handout section, together with the October issue of the What Now magazine and the SAIEE Training Academy brochure. I'd like to introduce you now to our host today, Prof. David Nichols, who is the chairman of the nuclear chapter. He was appointed as a chairperson of the board of the South African Nuclear Energy Corporation in January 2020. Prior to his retirement at the end of December 2018, he was the Chief Nuclear Officer at Eskom. Over to you, David.
Thank you very much indeed, Minx. And I'm really honoured to present Dr. Martin van Staden at X Energy. I'll first read the script, then I'll come back to it. He's the Vice President for Design Engineering at X Energy and was appointed in 2020 as the XE100 Program Manager to lead the non-recurring energy engineering development for the XE100 plant for deployment as part of the advanced program supported by US DOE. And they've got funding of up 1.2 billion from the Department of Energy. He currently leads the in-house design of approximately 250 engineers, supported by approximately 600 subcontractors across 30 organizations. That's a good introduction to Martin. I first met Martin when he was in Eskom, I think, doing computational fluid dynamics on the joys of Matimba Power Station. He then joined PBMR company and became an absolute star.
Correct.
At PBMR, driving the computational fluid dynamics side of thing. I think we can all be very, very happy with the stopped. Martin was transferred, took the ideas along with him and some other PBMR people like I think of names in a second, to go and take on the PBMR and take it to the States. So X Energy is really ex PBMR. So with that, I'm passing across to Martin to a presentation on the status of the reactor.
Thank you very much, Dave. Yes, and thank you to everybody that's joined. I'm really excited to present this. I've been really invested in pebble bed reactors since 1998 when I started working for Dave at PVMR. Yeah, when the project was cancelled, Ivan Mulder really came to me, and he'd been working on a small 100 megawatt design at the time at the university, and we said, let's see if we can get this taken further, and eventually got funding in the US to continue with this. Yeah, and I want to thank the chapter, the SAIEE chapter, for inviting me. I really appreciate the opportunity, and also thank you to Dumisani and IDC for sponsoring this event. I think we'll keep questions to the end. It just helps us manage the time a little bit better, but please make a note of the slide number, and we can always get back to the questions. Brief agenda, I'll introduce you guys to the XE100 reactor, just go over some of the fundamental safety aspects which are really important for this design, because it allows us to put the reactor very close to populations, as opposed to having a large exclusion zone around the reactor. Just go over the plant layout and some use cases that I'll just give some examples of how we're going to be applying the reactor in practice as well. So a really important aspect of our technology is that it's not actually new. It's actually pretty old. It started back in Germany in the 60s with the AVR reactor, which was the first test reactor for pebble bed based fuel. And I'll give you an idea of what the pebble fuel looks like in a couple of minutes. And then the Germans also developed the THDR reactor, which was a commercial scale demonstration plant that they built right next to the equivalent size coal-fired plant to demonstrate this technology. Unfortunately, it didn't operate for very long because of the Chernobyl accident, and that changed the politics in Germany, and they started shutting down all their nuclear, especially the new technologies that hadn't been operating for long. And then Chinese started the HDR-10 reactor in the late 90s, which was a test reactor. PVMR operated, started I think in the early 90s, got some decent funding in 1997, 98 timeframe, and got close to completing the detailed design of the plant that you see in the corner here, bottom right corner, before our funding was pulled. And then HDR-PM is a reactor that's operating today in China. We don't know too much about the operation of it, but we know it went critical and is operating very similar to the XE100 plant. However, I'll pull some notes up on how we've significantly optimized our design relative to the HDR-PM. The main type of technology we're looking at here is high temperature gas cooled reactor. We use helium as a coolant. These reactors can be classified as generation 4 advanced reactors, and there are a number of safety benefits as well as economic benefits that need to be met to be able to be classified as a generation 4 reactor. Back in 2015, we really identified any outstanding R&D needs. That was the first DOE grant X-Energy received for about $53 million, where we did a lot of further R&D on the fuel, and we developed our own fuel fabrication laboratory, and also started doing a lot of the licensing background and supporting R&D to support software codes and things like that. We really believe we've been able to use a lot of cutting edge tools that have allowed us to evolve our design to really get it cost effective and competitive, because that's probably one of the biggest challenges we've had in gas cooled reactors, is to get them competitive, and that's because they've generally got a low power density because you can passively remove the heat, and that is sort of challenges the economics, and unless you can take benefit from that and translate that into economic benefit, it's very difficult to make these economically feasible, and I believe that's what we've managed to achieve with the XE100. So really it starts with the fuel. I don't know if you guys can see my camera, but this is a Pebble fuel element. Gives you an idea of the size of the fuel element, and that's what you see on the screen here. Inside of this fuel, we've got about 19,000 what we call ceramic encapsulated coated particles. And the picture on the bottom right-hand side shows the white area there is the UCO kernel. And this little particle that you see here is much enlarged. It's only about 1 millimeter in diameter. So the uranium fuel is really in the center. We've got a porous buffer layer around the side, and I hope you guys can see my mouse. That is really the porous layer absorbs the majority of the fission products that are generated during the fuel utilization. And then we've got which is really the key retention capability of this fuel in terms of retaining the fission products. And this little particle is seen as a little pressure vessel. So we've got an inner pyrolytic carbon layer, a silicon carbide layer is a whiter layer in the center there, and then an outer pyrolytic carbon layer. And this is extremely important because we can retain approximately 99.999% of all the fission products within these coated particles. And that means we don't need to rely on huge pressure vessels and containment structures, because the fission products are retained really close to the source where they generated. Our design uses what we call HALEU, which is high assay low enriched uranium. We use 15.5% for our equilibrium core, and that advantage of that is that it gives us very high burnup, or very, very good utilization of the fuel. We get up to 160,000 megawatt days per ton of heavy metal on average. So the fact that we can retain fission products within the fuel elements means that we can really look at the design quite differently, and our safety systems are significantly reduced, and that's where we can draw benefit from a cost perspective. So this slide shows you a cross-sectional view of the reactor, and I'm not sure why my animation is not playing there. Let's see if it's going to go. So the XE100 is a 100 megawatt thermal, 200 megawatt thermal high temperature reactor. When you look at the animation on the side, I hope you can see that the arrows are showing the flow of helium. We use helium as a heat transport fluid to transport the heat from the reactor core, which is the center part in the Pebble, and that's where the name Pebble bed reactor comes from. The helium is heated up from about 250 degrees C to 750 degrees C. It then passes through a helical coil steam generator. This is a once-through steam generator with the water flowing in at the bottom. We preheat and superheat the steam in one pass, and get a high outlet temperature on the steam of 565 degrees C, which is similar to what we get on high efficiency coal-fired power plants. And that allows us to really utilize off-the-shelf steam turbine generator sets. So X-Energy didn't design any steam generator, any steam turbine generator set. We're buying this off the shelf from multiple vendors that have that size of turbine. Our design is quite conservative in the sense that as an advanced reactor, we don't need any new material code cases. We use ASME code cases that are existing. We don't challenge any of the temperature boundaries because of how we've designed the flow. So the pressure boundary is maintained at around 250 degrees C, which is quite low compared to where you need to go with some super high temperature reactors. That's it about in the reactor. What I didn't point out, what you see we also have 2 helium circulators that circulate the helium through the core. So those are really, other than the control rods, are the only moving parts on the NSSS side, on the nuclear steam supply side. We have a set of 9 control rods that insert into the side reflector. These are really just to trim the outlet temperature and control the outlet temperature to 750 so that we can maintain the steam temperature in a very narrow band. We also have 9 independent, what we call shutdown rods, which are used to shut the reactor down in cold conditions if we need to do maintenance. If we look at the thermodynamic cycle, what we see on the grey box is defined as nuclear island, and everything on the green box side is conventional island. From day one, we've designed this to be have a clear split, and we started with this philosophy back in 2015. EPRI is driving a big effort now to look at the splitting of conventional island and nuclear island. We actually started with that back in 2015. The reason this is important because we want to be able to have a physical and systematic split between the functions on the nuclear island and conventional island, because we knew that we're going to need to provide process heat, because this reactor is ideal for supporting industries like the petrochemical industry and others, to provide them with high temperature steam. And therefore, we wanted to envelope the use cases so that irrespective of whether you've got reactors, a steam generator, turbine on the back end, or a process heat plant, it shouldn't affect the safety case. So all our controls are taken from parameters on the nuclear island, and we don't need to control anything on the conventional island side. We could actually allow the customer, let's say the petrochemical plant, to actually control the entire process on the conventional island side. These just show a few of the parameters. If we go for purely power generation, we've got a plant gross efficiency of 43.1%, which in a net efficiency after house load has been taken off is about 39%. So that gives us just under 80 megawatts electric from the 200 megawatt thermal reactor. So we've done a lot of work over the last 10 years. As mentioned, one of our challenges in the design of these reactors is to get them economically competitive. And a couple of things that we've done, we've really used advanced simulation tools. My background is, as Dave mentioned, was CFD and finite element analysis. So we've been able to really take what we know from the neutronics with Dr. Eben Mulder and optimize the design around that to give us the most cost-effective design. To give an example, when we look at our pressure boundary, so this is a reactor, a picture of the cross-section of the reactor. The lower part of the pressure boundary in our reactor weighs about 200 tons. The HDRPM lower section, which is really represents the same volume, is 700 tons. So we've done a lot of optimization using advanced simulation, staying within the ASME codes, and we've been able to optimize the reactor significantly. Another area we've done a lot of work in is to improve the burn-up. I think HDRPM is running a burn-up of around 95 to 100,000 megawatt days per ton. Getting higher performance out of the fuel is really important, because the Pebble-based TRISO fuel is somewhat more expensive because of the low power density. So getting the maximum burn-up out of the fuel is a key contributor to improving the cost metrics of the plant. And then also, as I said, staying within existing ASME code materials has helped us reduce the amount of R&D required completely. Another key system is our fuel handling system. We have online refueling, which is a huge benefit, which means the plant doesn't need to come down, every 18 months for shutdown and refueling. It also is one of the reasons we can actually get to a very high burn-up, because we can measure the burn-up of every pebble and only remove it when it's really not going to contribute significantly to producing power. What you see on the right-hand side is really the highlighting the fuel handling paths. So we start up at the top with a fresh fuel loading that then using gravity rolls it into the fresh fuel loading block. It then rolls into this pipe that goes to the reactor. It's dropped into the top. It takes about 6 months for a pebble to travel through the core for one time. It then gets removed by one of these two augers. The next block is the burn-up measurement, where we evaluate the use of the fuel. If the fuel is then fully spent, it'll go up in one of these lines and end up in the spent fuel canisters. And then we'll replace it with a fresh fuel pebble. If it's not spent, it gets recirculated again and goes back to the marshalling block and gets inserted back into the reactor. On average, a pebble passes through about 6 times. And as I said, that's what really helps us get to a very high burn-up and improves our overall plant availability to around 95%. Once a fuel enters the fresh fuel loading station, no human interaction ever is required. Everything happens automatically. The fuel handling system operates automatically. And from there, the spent fuel goes to on-site storage vaults where it can just stand and through natural convection can cool down. We've got enough storage space, and I'll show the area in the plan view, to store 60 years of fuel on site. And there's no human access to those areas. We only use robotic machines to transfer the fuel from the reactor building to the spent fuel areas. And that makes our design extremely proliferation resistant. We've been working with the IAEA on that, and we've had very good results with the reviews that they've done on our plant up until now. The next important component is the steam generator. As mentioned, we've got two helium circulators that are placed on top of the steam generator. The gas coming into the steam generator at 750 degrees C, that shows the helical coils. The water inlet at about 193 degrees C then heats up the steam to 565 degrees C, and that's really allows us to do and 16.5 MPa high efficiency. And it also helps us to provide steam for a very large range of process heat applications, which is very important because we did a big trade study in 2015, and it clearly came out that process heat applications are going to be one of the big application areas in the future. And in fact, our first plant, folks might have seen on LinkedIn and other social media that Dow Chemicals is our first customer. We are actually on site today, started about 3 weeks ago doing the geotech borings and the water monitoring wells. And so the project is really a strong driver for Dow Chemicals as well, because they need this technology to decarbonize their product, and are getting a lot of pressure from customers in Europe and other places in the world where a carbon footprint is becoming ever more important. And we can literally plug in our design directly into the Dow plant and provide them with 3 different temperature ranges, and they also need power for that plant. So we've got an ideal customer there. They're used to building mega projects. We've got some of their project managers that have done multiple mega projects across the world that are literally in our offices every day, working with us to make this project successful. Another important aspect that we looked at is developing a very simplistic control system, because we want to minimize the operator interface. As happened in the aviation industry, the lower the workload of the pilots, the fewer pilots are required. You recall in the 80s we had 747s, and they needed 3 or sometimes 4 pilots. Plus a backup crew. Nowadays, all commercial jets only need two crew, and it's because of a lot of automation that has been built into the control systems. We've developed our own integrated modular automatic control called IMAC that uses control modules. So typically, we've got a startup module, a load following module, shutdown module, maintenance modules, and within those plant states, there are very set parameters that the plant cannot move out of. So that allows us to reduce the workload, so we don't have operators operating valves independently. They literally put the plant into the required operating mode, check that all the parameters are met, and hit the button to say it can continue into the next mode. So significantly reduces the load of the operators, and we're looking at up to 12 reactors that can be operated by 3 operators, and we already have been socializing that through topical reports with the US regulator and with the Canadian regulators, and not getting pushback on that. The table below here also just shows how simple our designs, our control scheme has been designed. We've literally only got 4 control variables, so the helium inlet temperature to the steam generator, the main steam pressure, the main steam temperature, and the electrical load. And as I mentioned, what you see on the right-hand side where I'm circling my mouse there, that's the main steam control valve to the turbine. The customer can do with that valve what they want, and the plant will merely react to the temperature and pressure in that feed line. If you close the valve, the pressure increases, and our control system will automatically recognize that and reduce the power on the reactor side. So a very simplistic control system, no complex control loops, and that's also a big improvement from when it comes to regulatory review of the distributed control system. So this has been so much simplified that our control system there's no safety related component in our DCS, our distributed control system. The only safety related control part is our reactor protection system, which really just trips various aspects of the plant. So that's helped us also reduce costs significantly on the nuclear island. This slide here gives you an idea of a mock-up mock-up of our control room that we've used to develop the human interfaces and control. So we are now busy building out a full-scale training facility that will be coming into operation in December this year. We're 99% completed with that build, and that'll help us lay the footwork for starting to train operators, the trainers that need to train operators, as well as the nuclear regulator. But this just shows a mock-up of the four reactor plant, showing the shift supervisor in the center and 2 reactor operators, each looking at 2 modules. On the conventional island side, we've only used off-the-shelf equipment. The top right-hand corner there is the Siemens SST 800 steam turbine generator set with its auxiliaries that comes as, I think, 3 or 4 skids to the construction site. It's installed in literally less than a month, and so that's a really easy install, no development work on our side to do that. It's a high efficiency turbine at 42.3% thermal efficiency. Condenser cooling, we can use anything from something like these wet-cooled, forced wet-cooled modules on the bottom right-hand side. In fact, the plant that we'll be doing for Dow in Seadrift, Texas, will be using air-cooled condensers like at Matimba and Medupi and Kusile, because it is a water-strained area. And obviously that will drop the efficiency a bit, but we believe that wet cooling is really difficult in many areas of the world to get approved. So having a fully dry cooled solution is a huge benefit as well. So give a little bit of a look out of what the plant layout looks like. We've focused on a standard four reactor plant layout that gives us good economy of scale in terms of the operational costs. We can go up to 12 reactors on a plant, meaning that only the same number of support personnel will be required for 12 as is for 4. We can do a single module. The running costs do increase slightly because you're not spreading that across you know, 4 reactors. So the optimum, we start reaching optimum point at 4 reactor modules. What is important here, if we look at the red line, a red box, this is called the protected area boundary, and that's part of the physical separation between nuclear and conventional island. That means all the maintenance that's done on the turbine side, which is actually the driving maintenance on our plant, is the conventional island side. All that maintenance can be done by standard contractors that you would use for coal-fired power plants. They don't need special training or anything like that. So that's another component where we've managed to reduce cost. And also because of the limited size of the protected area boundary, we need fewer security guards from a nuclear safeguards perspective. When we look at the APZ, which is a blue line, we are with our source term calculations. In other words, if we have a worst case accident and we release all the helium from the pressure boundary, we can still meet the regulatory requirements at our site boundary limit. And that's a huge benefit and part of the reason why we can now locate a plant like this close to populated areas or close to a process heat plant to be able to achieve that. We also have spent fuel storage for 60 years of operation. We've got 1 storage area per reactor so that you can build out the reactors in series. In other words, you can start a plant with 1 reactor and 2-3 years down the line start construction on the second one. We've literally spaced the reactors out sufficiently so that the constructors can actually achieve that without impacting the safety on operating reactors. Just another slide of the site layout that numbers all of the buildings, and we will provide the presentation afterwards, and gives you an idea of the size of the plant, around 27 acres. It does depend on whether you use air-cooled switchyard or liquid-cooled, gas-cooled switchyards. So you can reduce that footprint, and also obviously depends on dry or wet cooling. The picture here shows wet cooling towers. This is part of the smart plant view of the same picture. So these are the reactor buildings are predominantly subgrade. You don't really see them. They're these gray sections that are sticking out under the orange bars. The orange building is just showing the structure of the building here without cladding. So we can see inside. That's called our Nuclear Island Auxiliary Building. And all the safety related equipment is within the reactor building, which is subgrade. So and everything in the Nuclear Island Auxiliary Building is non-safety related. So that means, once again, you've got a lot of cost savings by having non-safety related systems when it comes to work and maintenance that needs to be performed. These 4 buildings that are similar here are the spent fuel storage areas. We've got our rad waste treatment, our control and electrical building, and then a workshop and our helium storage area in the bottom here. And the yellow buildings are the turbine buildings. And in fact, for the Dow plant, the turbines are actually going to be outside because petrochemical guys don't put stuff in buildings. So they said, why do they need a building? So we're not even putting a building there. So looking at cost savings there. I want to quickly go over some safety aspects, and the main way that we've managed to reduce cost is by minimizing the number of safety systems. We only have 6 safety systems in our plant, of which the fuel is one of them. When we compare that to even advanced light water reactors, they've got about 30, and conventional reactors like Coburg, Dave, you might know better about, I think they've got around 60 safety systems. And so each safety system means there's a lot of quality assurance that's required for fabrication, for maintenance, for monitoring, and all that increases cost. And by minimizing the number of safety systems, we've been able to reduce the operating cost significantly. So a lot of the safety is actually handled by the fact that our fuel retains sufficient products, and these pebbles are graphite, and they can withstand temperatures of almost 2000 degrees C. In fact, when we make the fuel, the graphite is graphitized at around 1950 degrees C, so 1950 degrees C. So we know the fuel can handle these very high temperatures without being damaged. Another important safety feature is that our primary shutdown mechanism is actually built into the design, and it's called the negative temperature coefficient. So what does that mean? That means that as the reactor heats up, the nuclear reaction will actually shut itself down. So this is a typical Evan-Mulder graph, and most probably a little bit intense for you know, a public sort of presentation. But what this shows is the different coefficients that contribute to the total reactivity. And so we've got the Doppler coefficient, which is the blue line. We've got the moderator coefficient, which we've got a graphite moderated reactor, and that's also a function of temperature. And then we've got the reflector coefficient, which is really looking at how well the reflector reflects neutrons back into the core. And when you add these three together, we can see that overall we've got a negative temperature coefficient over the full operational range. And that means the moment you stop cooling the core, this reactor will shut down. You can actually load follow the reactor by just changing the mass flow of helium that goes through the reactor. The only reason we have control rods is to trim the outlet temperature. So our primary shutdown mechanism is the strong negative temperature coefficient. And this is a huge win we've had with the nuclear regulator to accept the negative temperature coefficient as the primary shutdown mechanism. The regulator requires two independent means to shut the reactor down, and the negative temperature coefficient being one, and we use our shutdown rods as a secondary system. And they also are inserted using passive means, so we simply cut the power and they will drop in under gravity. The second safety feature that's really important is removing decay heat. So even once your reactor is shut down, it's generating decay heat. And in fact, in Fukushima, the reactors were shut down, and it was the decay heat that was, even because they couldn't continue cooling the core, the decay heat was sufficient to actually melt the core. So in our design, with the low power density, we're able to dissipate the heat into the environment. So that takes the heat through from the pebble bed into the graphite structures, through the core barrel, into the reactor vessel, and then through natural convection into the atmosphere. So that means that no operator action or active system is required for safety. That also means we don't have any Class 1E electrical system. Class 1E are safety-related electrical systems. We don't need a safety-related diesel generator as a backup. This is also another cost-saving area where we can reduce costs significantly. Safety-related electrical equipment can be three to four times the cost of non-safety-related equipment. So just a couple of areas where we really feel our design is well suited for the electricity generating environment of today. We know that future grids are going to have a significant amount of intermittent wind and solar, which results in a lot of grid instabilities. Our design is very well suited to provide either base load, beg your pardon, or load following, to really support a grid that has got a lot of solar. And the picture you see here is really from California, where during the day they've got the solar that kicks in. Sorry. So the yellow line is the solar that comes on load. You can see between 7 and 8 o'clock in the morning it starts picking up. But unfortunately, in the morning at 6 o'clock already, when we look at the blue line, the load starts picking up because people wake up, they shower, they make food, start making food. And then during the day, you've got all your industrial load that needs to be carried. And then in the evening, people once again go home, you know, heaters go on, start making food, and you've got your evening peak. And this is really typical for many grids that you've got a morning and an evening peak. And unfortunately, the sun doesn't shine during those times. So what we demonstrated, and we've got wind in the green, you can see there's a reasonable degree of intermittency, but not as high as the solar. So on this grid, it was really important for whatever other source you added to be able to load follow and take up the load and be able to slow down. And we modeled this red curve with the XE100 showing that if you had XE100s on the grid, you could fully stabilize the grid with this amount of solar, which is significant. As you can see, the solar itself is the largest portion of power production during the day. And having the XE100 would allow you to really stabilize the grid. You also have the opportunity with the XE100 to place it in multiple places, you know, also reducing grid stability, so having more distributed power. This slide here just shows how we can load follow. So the black line is the load demand, and the red line is the normalized turbine power. We also plotted the steam pressure and the steam temperature on the right-hand side, and just showing that how we can actually load follow and meet the load demands of the grid. And we can run at 100, 40, 100 load following indefinitely. There's an effect called xenon poisoning, which occurs when you change power. And we've designed the reactor to overcome that. In fact, we can probably go down to as low as 25% power, but we've limited at this stage to 140, 100 as a claim where we can load follow indefinitely as much as you need. We also have a very high ramp rate at 5% per minute, which is similar to what you really can get with gas-fired plants as well. So I've added this slide as I think as a closing slide. This is an example of the Sasol Secunda site, and some of the, just to give an indication, they've got around a 3 gigawatt requirement. Now, I've not been able to get the exact amount, but approximately 3 gigawatt, 3.2 gigawatts. So showing there the footprint of four-pack reactors next to the Sasol plant, and those 16 reactors can effectively decarbonize most probably 99% of the Sasol plant. So and the distance between the reactors and the plant can be, you know, minimized in the way I've shown here. From a regulatory perspective, on the nuclear side, that's not an issue. Typically at the Dow plant, we're about just under a mile away, but it's just because that was the closest site that we had. And even at a mile away, it's quite efficient to use our reactors for process heat of the Dow plant. So in summary, we believe our XE100 is a low-risk design based on proven technology, and we've done a huge amount to optimize that and ensure that it is cost-effective even in the US and compared to natural gas power generation. The fact that we've got a very small EPZ means that we can deploy the reactors close to densely populated areas or in remote areas. The fuel retention capability is really a key piece of our intrinsically safe design. I've shown there that we can provide base load or load following, and also provide carbon-free process heat. Yeah, and finally, you know, we're looking at target market deployment in the late 28-29 timeframe. We are targeting having the first reactor fully commissioned in the first quarter of 29, and about a 3 months difference between units 1 to 2, 3, and 4. So thank you again, SAIEE, for inviting me. I hope this was valuable to everyone. And also thanks to the IDC for sponsoring this. There's a bit of an animation that's probably about 2 years old, but just gives an idea of the plant and we can watch that while I open up for questions.
Thank you, Martin. Absolutely excellent. I should almost say son of PBMR. There was so much PBMR philosophy in there. Some improvements, but I'd argue. I don't see any questions yet. So while I'll just do a couple of questions that I've got, and in no particular order. The first one is the reflector in your reactor changeable, or is it a life-limiting component?
That's a great question, Dave. We've actually got a patent out on our side reflector. So we looked at for guys that don't know that because of the neutrons that continually bombard the reactors, the side reflector, which is graphite, the graphite changes shape. It actually warps, and that limits the lifetime of the graphite because it also induces significant amount of internal stresses in the graphite. And so we did a lot of optimization by modeling the material properties, and we developed what we call almost a tile that limits the amount of graphite that needs to be replaced. So we do have a midlife outage where we replace only about 10% of the side reflector graphite. Because we've got this, we've optimized where we cut that tile. That's a big difference between our design and what I believe the Chinese have done with their reflector. So most of the graphite will see the 60-year lifetime.
Okay, excellent. So you are, I don't think it's nice because people who build plants and say it'll last, the graphite is, I mean, the UK AGRs are closing down because of graphite issues now. There's no other good reason to close them down. But okay, yeah. My second question is in no order. Is you've got online fueling. You don't. What is your expected shutdown interval?
6 years. And
of your reactor.
Yeah, our shutdown or our intermediately sized maintenance is for the turbine maintenance. And so it's not driven by the reactor like in light water designs where you have every 18 months you have a shutdown, then you can do the other maintenance as well. In our case, we're doing only a 6-yearly maintenance. We are doing all our fuel handling system maintenance with robotic tools, so we don't need to shut the reactor down to do that. The fuel handling system only operates at full power for about 8 hours a day. So that means we've got about 16 hours a day to do maintenance on fuel handling if required. We can also actually stop fuel loading for about a week and continue with full power before we start running out of reactivity. So there's a lot of leeway to do online maintenance while the reactor is operating, and we've designed it to do that to minimize downtime on the reactor side.
Okay. One last question. There's one question in the text that I'll come in, and that is the Chinese are looking at putting multiple reactors with SGs feeding a single turbine to get a more efficient steam turbine system. Have you ever thought of that approach, or do you think it's not worth it?
Yeah, that was a really interesting one. We did a trade study back in 2015 to evaluate that. And although a single turbine is slightly more cost effective, when you look at the capability to actually start generating power from unit 1 and 2, and also the fact that when you take down, because the turbine drives the maintenance, when you bring one reactor, when you bring the turbine down, you're bringing down all the reactors. And our economics show that even just during commissioning, the fact that you can start up the reactor most probably 3 months before the second one and the third one already just counteracts the capital cost difference. And then there's the aspect of availability. So when we come down for maintenance, we only bring down 25% of the plant for maintenance. If you had one reactor, multiple reactors feeding a large turbine, you're bringing down the whole plant. And so when we did those studies, it became clear to us that having these individual modules And that's part of modular reactor design, sort of 101, is that you want to achieve that modularity on an operational scale as well. So yes, we did look at that.
Okay.
We decided against it.
Yeah, it's interesting because I'll do a bit of, you know, I was there at the beginning when we and PBMR, the phrase PBMR was developed, I know very well, because it was over a weekend when I had to write a report. And the word module there was very much seen as, for the utility point, having modules of, in that case, I think it was then at that point, 60 megawatts or something, very similar to where you are now. There's a question from Rob Winstanley, which I can half answer and I'll pass it to you. Is helium a readily available resource? Is it not a limited resource?
Yeah, also a great question.
Can I add to that question, Martin? What's your leak rate? So I'm going to add to that question. What's your expected leak rate of helium from the system?
Sure. I need to go out and eliminate. I think it's 0.1% per day, something like that.
Was point.
Sorry?
It sounds like the PBMR number.
It does, because I mean that's some of the. It's really based on the German data as well. So you know, we are building a helium test facility in which we'll be testing that, because most of the leakage really comes through the helium after the fuel handling system. So it's not very high, and we really seal well all our flanges and all the valve our valves. As well, we use bellow actuated valves and things like that to minimize leakage. On the question of helium availability, we've been doing really on a yearly basis. We do an update on helium supply chain. We're working very closely with Linde and a couple of other companies. Currently, we don't see any shortage of helium. There were some questions about the availability of helium, and the US, just to point out, the US used to maintain helium as a strategic resource, and they've actually released their resources now because they don't see that as a limited critical strategic resource anymore. It's a very good resource, but it's the amounts of helium that are available today are exceedingly high, and the study we did showed that, you know, for the next 60 to 100 years, we don't expect any problem with helium supply.
Yeah, I just add to that. You're aware that we've had a new helium discovery in the Free State?
I did see
which
that,
is now going on with some amazing percentage of helium in the gas. Just of also interest for those who believe helium can't be kept in, I will comment that the helium test facility at Pelindaba, which was last operated in 2010 and has all bolted flanges, because it was not, they weren't welded in, they were bolted because we had equipment for test and still do. We haven't recharged that facility since it was shut down in 2010, and it's still holding pressure now. So we've held pressure in that circuit for 13 years. It is going down very slowly, but helium leakage is not an issue. Just of interest on helium, just for those who are listening, there were some real horror stories on helium, and the worst horror story was the Forts and Drain reactor in the USA, which I think lost its charge, 100% leakage about every couple of weeks, basically. But that was because of the design. It was simply because it was not a very clever design.
That's correct. We took a lesson learned from Fort St. Vrain. They had a steam-driven helium circulator, and sealing between the circulator turbine and the helium side was really almost impossible, and they had significant problems with those seals that resulted in large amounts of leakage.
And also water ingress to the primary circuit, so you end up with corrosion of a long story there. Okay, I'm looking carefully. I see no more questions. I think that it is very, Martin, it is wonderful to see the PBMR philosophy going on so well. I would argue that this is where PBMR almost was in some ways, not completely, but was literally in the 2000s.
Correct.
Wish we had gone forward with it. But don't get me, I'm so pleased that you and Eben took it over to the States and made it happen. My only question is, what export controls have you got on the technology?
Yeah, so I mean the challenge at this point most probably is the 123 agreement between the US and South Africa. That I don't think it's been signed yet, because anything on the nuclear island, well, not anything, anything on the primary circuit is nuclear export control, and obviously the fuel falls under IAEA safeguards. So there is export control requirements on this, on the nuclear island side.
Yeah, I think it could well be a challenge going forward. I would have argued that we should have had export controls on you guys going to the States, but I'll pass on that.
A bit late now.
I see no. Sorry, it's a bit late. No, I mean, and the basics were all basically put together by the. There is no fundamental big secret here. It was all put together by the Germans. People might refined it further with public information. The Chinese have actually built one. I don't know the details of it. I know some information about it. And you're going on brilliantly. And I think it's very exciting. And USNC, of course, theirs is not Pebbles because they're not doing any fuel movement. But anyway, okay. I'm now looking. Minx is offline at the moment. There's been some problems on her network. So I'm going to ask, I'm going to thank you very much indeed. We've been going for an hour. Thank you, Martin. Excellent, brilliant talk. Really happy with that. I'm just annoyed that it shouldn't be built. We should have a 4-pack in Cape Town, not in Dow Chemicals. But let's not go down that line too much.
Let's hope we
and
can,
any last? Sorry?
Let's hope we can bring it back to South Africa, Dave. I'm really working hard to find a route back to South Africa. We've had multiple discussions with entities in South Africa when I was there in September. Investec set up a meeting with us, and we had some good audience there with large power users. And we've actually got some folks coming over here in the next couple of months. So we're hoping that we get the 123 agreement signed so that we can take this to the next level, because I really think there's a lot of appetite for this in South Africa. And given the size of the project, we believe it can be funded privately, setting up a consortium and using World Bank funding to finance it. We really hope we can get a project going in South Africa.
Excellent. I will just comment that it's well known publicly that Nexa, which of course I now chair, has taken a position, and publicly so, that we wish to get back into the small modular reactor business, with the first of class being on our site at Nexa. And then our view is that yes, there's clearly the Sasol's as well, but on a bigger distance, we have got a whole pile of coal-fired stations which are going out of service because of old age, and we could use those sites to build. We could repower them. I always like the phrase repower. People think it's like putting a different spark plug in a car. They don't realize that repowering a power station involves a bulldozer flattening everything in sight, and you build a new one.
We've looked at repowering a lot. We actually, there's a public study on a coal-fired plant in Maryland that we are looking at repowering, but really utilizing the site infrastructure in terms of water and grid connectivity, and the environmental impact assessments to use those. We don't believe it's feasible using the steam part of the old plants, because it's already old, and that's only 10-15% of the cost of our plant. So
can't agree more. But everyone has this vision of somehow you're going to put a nuclear power station into the old building.
Old coal-fired plant, no ways.
No, I wasn't going anywhere close to that. Okay, well, with that, I'm going to say thank you very much indeed. Thank you, Dumasani, for sponsoring it. And I hope we see action. We have a new IRP coming out shortly, we understand, and that might give us some exciting things. So with that, I'm not sure what button to press. I'm going to close this thing. So thanks, Martin. Thank you, everyone attending.
Thank you.
Please have a good day. Okay. Cheers, guys.
Bye.